The histogram-based methods are more powerful than simple mathematical operations. Here we will study what image histogram is and how we can manipulate them to get better results. Two prominent techniques are histogram stretching and histogram equalization. But let's first discuss what the histogram is. A histogram is graphical representation of discrete data distribution. The horizontal axis represents some parameter value and the vertical axis shows its frequency. Frequency means the number of times a parameter occurs in our dataset. Let's say we have a 6 by 6 image having 8 levels ranging from 0 to 7. The number of times each level occurs in the image is called its frequency, and its corresponding histogram is shown in the figure. Levels 3, 4, 5, and 6 are not present in the image, so their frequency is 0. Whereas level 0 occurs 18 times, so its frequency is 18. Similarly, the frequency of level 1, 2, and 7 is shown in the figure. It is often convenient to normalize the histogram to get the better interpretation. In this case, rather than taking the count of the gray levels, we use their normalized value. A histogram provides information about the darkness and contrast of an image. A positive skewed image is darker than negatively skewed image, and an image with good contrast is distributed equally. Here, uh, image second last image from the bottom has low contrast, and whereas the bottom image has high contrast, cause its histogram is well distributed well. A histogram might not be a true representation of the image. Three images shown in the figure may have same histogram as there is same amount of white and black level, but they are totally different. Given a poorly contrasted or a dark image, we would like to improve its contrast or lighten it. We can do this by histogram stretching and histogram equalization. Let's discuss both of the techniques one by one. Histogram stretching aims to increase the dynamic range of the image. The task is achieved using a piecewise linear function. It has three parts, typically slope of the middle part. Here from R1S1 to R2S2 is different from rest of the two parts. Other two parts are from 0 to R1S1 and R2S2 to the final level. Shape of the transformation function is controlled by R1S1 and R2S2. If R1 and S1 are equal and R2 and S2 are equal, then it would be a simple step function. Sorry, it will be a linear function. It may have no effect on the image contrast. If R1 is equal to R2 and S1 is equal to 0 and S2 is equal to L minus 1. Here, the function will be a simple step function. So the resulting image will have only two levels, 0 or L minus 1. If they are less than R1, then they will be black, otherwise white. The interesting case is where R1 is less than R2 and S1 is less than S2. Then it will form a shape somewhat similar to the shown in the figure. Here all values on horizontal axis are being stretched to a wider range, resulting in a well-distributed histogram and consequently a better contrast image. Let's analyze the effect of histogram stretching. The image A shown on the top left is low contrast image. Its corresponding histogram is shown in figure B. We apply the transformation operation shown in the figure on the left side. This results in stretched histogram, and the resulting image is shown in figure C. The limitation of histogram is to select the transformation function manually. We have to select the value of R1, S1, R2, S2 by ourselves, which may not always be an optimal value. Another histogram-based approach is histogram equalization. Goal of the histogram equalization is same as that of histogram stretching, that is distribute different levels equally. But the beauty of the technique is that it does the job automatically. No manual input is required, you just have to follow a sequence of steps and result is well-formed image. There are two conditions for the transformation function in histogram equalization. It should be monotonic, that is, its value along the x-axis should not decrease, and its range should be between 0 and 1. A typical transformation function fulfilling the condition is shown. We don't select it manually, we obtain it using a well-defined procedure. Let's discuss the procedure. The first step in histogram equalization is calculating the cumulative frequency. The cumulative frequency of each level is sum of cumulative frequency for the previous level and its own frequency. Cumulative frequency of level 0 is equal to its own frequency. Here level 0 has the frequency 5, so its cumulative frequency is also 5. Cumulative frequency of level 1 is 11, as its cumulative frequency at previous level is 5, and its own frequency is 6, therefore their sum is 11. A typical histogram is shown on the left, and the resulting histogram after applying the cumulative frequency operation is shown on the right. You can see that its height is never increasing, is never decreasing, but increasing from left to right. Next, we calculate multiplication factor. The factor is equal to L minus 1 divided by S, where S is the sum of the frequencies. That is total number of instances in our data set. A histogram is shown in the figure. It has 16 levels with different frequencies where the sum of the frequencies is 360. So the resulting factor will become 1 over 24. We multiply the cumulative frequency with the factor and round the resulting values. The fourth column shown in the figure here shows the result after multiplication, and the fifth column results show the rounded value. Original histogram here on the left, along with the resulting histogram after applying the histogram equalization operation is shown in the figure. Resulting histogram is well equally distributed while compared with the original histogram. One may observe that the distribution is not perfectly equal. It is better than the previous one, but not perfectly equally distributed. The reason is that the speed frequency. The result might be better for the continuous values operation. Results for applying histogram equalization are shown. Resulting image is much better than the original image. The operation we discussed so far apply transformation function based on the entire content of an image. Sometimes it is necessary to enhance the details or small areas of image. The histogram processing techniques are easily adaptable to local enhancements. We apply the operation in small regions. It's not compulsory that the regions don't overlap. We may apply the operation on overlapping regions as well. The results for applying global and local histogram stretching operations are shown in the figure. Left one is the original image with very fine hidden details in it in the black boxes. In the middle, we apply the global equalization operation and thus, whereas on the right side, we apply local equalization and get better results. We can see that here there are much prominent in the right side of image and we have applied the local equalization. During the transformation operation, we have to calculate each pixel value using transformation function. This might be a costly operation and it may take time. A nice idea is to calculate all of the level values for given transformation function from 0 to 255 ahead of time and so store the result in some table. You may call the table the lookup table and use the lookup table to calculate the value at runtime. An example lookup table is shown in the figure. The table maps the value 40 to 90 and 30 to 10. There may be a plenty of examples. User may develop lookup table as per their requirements. Thanks.